Greetings, Mr. Sutton here, bringing you the AB Calculus 3-7 Extra Practice number 4 solutions on the chain rule. On this calculator-based free response problem, we have this table showing us values of a twice differentiable function f and the f prime derivative of that. And we have this g function that they're randomly giving us, which is defined as f of x squared minus x. All right, so given all this, our first task is to find the value of g prime of 3. Well, here's the g function again. To take the derivative, since we have a function inside a function, we're going to have to use the chain rule. So we have the derivative of the outer function, which is just going to be f prime of all this stuff with no change in there. But then we have to multiply by the derivative of the inner function. So derivative of x squared minus x, that's going to be 2x minus 1. So there's what g prime looks like. We still don't have a whole lot of clarity on what f prime and f are doing, except that they gave us some table values, so hopefully those end up helping us out. All right, so let's go ahead and find g prime of 3 now, just plugging 3 in for all the x's here. And when we do that, we see that we are taking f prime of, let's see, 9 minus 3, so that's f prime of 6. And over here, this is going to be, let's see, 6 minus 1 is 5. So we have f prime of 6 times 5. Now, f prime of 6, let's hope that that's in the table. It is. If we look at the x value 6 in the table, f prime of that is going to be 4. So this is really 4 times 5, which comes out to 20. On this part of the problem, they're telling us that it is known that g double prime of 0 has a value of negative 1. Based off this, we want to know the value of f double prime of 0. So let's just review what we have to work with here. So if we're saying g double prime of 0, that means that if we figure out a formula for g double prime of 0 and plug 0 into it, we should be able to set whatever that is equal to negative 1. Now, where this ties in with this f double prime of 0, you'll notice that the g function is at least partially defined with the f function sort of thrown in there. So perhaps in the course of taking g double prime, we end up with an f double prime that we can then solve for when we set all this craziness equal to negative 1. That's the strategy anyway. Now recall from part A, we already found the first derivative of g. Again, that was f prime of all this stuff times 2x minus 1. So in order to find g double prime, we're going to have to use the product rule here. So that's u prime v plus uv prime, just to review. And let me set up my box and ribbon to help me manage all that stuff. So my two factors, I've got f prime of x squared minus x in my upper left here. Upper right, I'm going to put the 2x minus 1. And down here, I'm going to put the derivatives of these things. So derivative of f prime x squared minus x, that's going to be f double prime of that stuff, times the derivative of 2x squared minus x, which is, again, 2x minus 1. Next, derivative of 2x minus 1, that's just 2, so a little bit easier there. Now, before I actually multiply all this stuff out, I'm going to plug in 0 just to see what I'm dealing with. Then I'll sort of plug it into this general format and set it equal to negative 1. But let me plug 0 in inside the box here, just so it's a little easier to stay organized. All right, so we've got f double prime of 0 squared minus 0. That's f double prime of 0. Now, we don't have to leave it like that because we actually know what f double prime of 0 is from the table. Looking it up in the table here, that's going to have a value of 2. So let me put 2 in there. If I can at least get some constants that are defined, I'm going to be ahead of the game here. Now, for the next one, we have 2x minus 1. If I plug 0 in for this x, that just leaves me with negative 1. Down here, we've got f double prime of 0, basically, times this is going to be negative 1 if I plug 0 in there. So this is negative f double prime of 0. I don't know what f double prime of 0 is, but here's the good news. That's what I'm actually solving for. So just like I predicted, we get an f double prime of 0 that pops up in the course of trying to take this second derivative for g double prime. Anyway, moving on to this last piece here. 2 is a constant, so that's just going to still be 2. All right, let me use the ribbon to multiply all this out. So we have negative f double prime of 0 times negative 1. That's just positive f double prime of 0. So this is g double prime of 0 now that we're writing out based on this product rule formula here. This was u prime v basically. Now for uv prime, going the other direction with my ribbon, I'm going to have 2 times 2, so just adding 4 there. And they said that g double prime of 0 has a value of -1. So let's set that equal to -1. So here's the really good news. To get f double prime of 0, I just have to isolate f double prime of 0, which means all I have to do is subtract 4. F double prime of 0 then has a value of -5. On this problem, they're asking if there's a c value between 0 and 3, and c is just an x value, such that g of c equals 5. Justify. All right, so this is one of those intermediate value theorem problems. They're asking if there's a certain output that we can get over a certain range of inputs. So in order to do this problem, if you're going to use the intermediate value theorem, which is really the go-to theorem on these, you need to show that you have continuity over this interval, the closed version of this interval, and you also need to show that the value you're looking for, 5 in this case, lies between the beginning and ending y values on this interval. So let's start with the continuity piece, because we have to actually mention or prove that we have continuity before anything else matters. So do we know for a fact that g is continuous on the interval from 0 to 3? Well, let's take a look again at the g function. So it's f of x squared minus x. X squared minus x by itself is just a polynomial which is known to be continuous, so that's not going to cause any issues. How about the f function? Well, they said here that f is twice differentiable. So if f is differentiable, let alone twice differentiable, and x squared minus x is differentiable, it certainly is, it's a polynomial, it's differentiable, it's continuous, all of that, then that proves that the g function, which is comprised of these things, is also going to be continuous. So we've got continuity for the g function because f is differentiable and x squared minus x is continuous and differentiable. Next, we have to take a look and see if 5 is between the beginning and ending y values. So to find those, we need to find, first off, g of 0. Now, g of 0, if you just plug 0 in here, that's actually f of 0, because you have 0 squared minus 0. And f of 0 we can look up in the table. That has a value of 4. Now let's check out g of 3. That's going to be g of 3 squared, or f of 3 squared minus 3, so f of 6. And we can also look up f of 6 in the table. That's 7. 4 is less than 5 is less than 7. 5 is between 4 and 7. So therefore, by the intermediate value theorem, we're guaranteed that g of c equals 5 for some c value on the open interval from 0 to 3. For this last task, they're saying that h is the function whose derivative is given by h prime equals 4e to the cosine of x. That's really lovely. We're probably going to have to put this in the calculator in a minute. At what value of x in the interval -3 to 0 does the IROC for h equal the average rate of change, the AROC for f, over the interval -3 to 0? So at some point we're going to have to use a calculator here. We're going to have to figure out where the h prime equals the average rate of change of f. But before we can do that, let's actually figure out the average rate of change of f over this interval. So that's going to be f of 0 minus f of -3 over 0 minus -3, or 0 plus 3. So that's going to be, let's see, f of 0 is 4, f of -3 is -5, so we have 4 plus 5 over 0 plus 3. That's 9 over 3, which is 3. So basically, we want to know then where h prime, the instantaneous rate of change of h, takes on a value of 3. So let's do this on the calculator. So here I am in the y equals. I've put the h prime as my y1. The average rate of change is 3. That's my y2. And let me use a window from -3 to, let's make this 0. And let's do zoom 0, zoom fit. And hopefully we get a good picture of that intersection. All right, so here's our h prime. Very exponential looking. And then there's the horizontal line through 3. Now let's see where these are actually intersecting. So second, trace option 5 for intersect. And let's just move a little closer. Enter 1, 2, 3 times. Gives us a value of -1.863. So there's my intersection. Let me write it down. X equals approximately that. And we're done. On this problem, we're given that f is differentiable and h is 2 plus f of sine of x, and all of this is being cubed. Based off this, we just want basically h prime. So we're going to have to use the chain rule on this one. The outer function is this cubing, so we have 3 times something to the second power. In this case, 3 times 2 plus f sine of x, all raised to the second power. And then we have to multiply by the derivative of the next function in. So the next function in is 2 plus f of something. So that 2 is going to get differentiated away, constant becomes 0. And the derivative of f of something is going to be f prime of the something. So in this case, f prime of sine of x. Finally, we multiply by the derivative of the innermost function, which is sine of x. That derivative becomes cosine of x. All right, so these are the links in our chain. Let's see if we have an answer choice that reflects that. So A, definitely not. B, we needed the last tail there. We didn't get the cosine. C just has the wrong thing inside of f prime. So really, it's D is the only one that's going to work here. On this problem, I'm trying to take the derivative of this expression here. Now, I've got a product going on and also a chain rule because I have secant of 2x. So I'm going to have to use the product rule on this along with a little bit of chain rule action. So that's going to be u prime v plus uv prime for the overall format. Let me get my box and ribbon out here. And my two factors, I've got x cubed and secant of 2x. Derivative of x cubed is 3x squared. Secant of 2x, that's going to be secant of 2x tan of 2x times a tail of 2. Now multiplying all this out with the ribbon, I've got 3x squared secant of 2x plus x cubed secant 2x tan of 2x times 2. I guess you could make it 2x cubed. That 2's got to go somewhere, and that should do it for this one. So let's see, do we have an answer choice that reflects this? We need a 3x squared and a secant of 2x, and it looks like they wrote these in opposite order. The 3x squared is going to come second. So let's look for 2x cubed as the first term. And it looks like we've got answer choice D has everything we're looking for. Well, D it is. On this problem, I'm trying to find the derivative of 2 sine of radical x quantity squared. Let me start by rewriting the original function as 2 sine of x to the 1/2 whole thing squared. And then I'm going to need to use the chain rule on this one. So my outermost function, I've got 2 times something squared. Derivative of that is going to be 4 times something to the first, so 4 times sine of x to the 1/2. Next, I multiply by the next function in, which is sine of something. Derivative of that is going to be cosine of something, so in this case, cosine of x to the 1/2. And then we've got the innermost function, which is x to the 1/2. Derivative of that is going to be 1/2 x to the negative 1/2. All right, now we have to convert this into a form that we recognize here. So if we simplify everything that we can here, because of this negative exponent, we're going to end up with some kind of fraction. I've got a coefficient of 4 here. Over here I've got a 1/2, so that can become a 2 if we multiply those together. I've got sine of radical x, if I turn that back into radical form. This is cosine of radical x, and we'll just be glad they don't ask us to convert this into a double angle here. I guess you could write this as sine of 2 times radical x, but they're not going that far. Now in the denominator, we have this x to the 1/2 getting moved downstairs, so we have a radical x in the denominator as well. And looking at our answer choices, it's looking like D matches that stuff exactly. For this one, we have this h function, which is 1 plus f of 3x the whole thing squared for some differentiable function f. We want to know basically h prime. So for this, we're going to use the chain rule. We start with basically something squared, and the derivative of that is going to be 2 times the something to the first power. So 2 parentheses 1 plus f of 3x. That's going to be the first link in our chain using the chain rule. Next, the derivative of the inner function here, which is 1 plus f of something. Well, the derivative of that is just going to be f prime of something, so f prime of 3x. And then finally, we need to multiply by the derivative of 3x to get that last tail in our chain here. So that's just going to be 3. Taking a look at the answer choices, well, the only one with that tail of 3 ends up being choice D. So for this problem, we're asking for which of the following functions would quotient rule be considered the best method for finding the derivative. So let's look through each of these and see what technique seems to be required here. For this first one, definitely not a quotient rule. This is a function inside a function, so chain rule would work there. For choice B, you could use the quotient rule, but it's kind of the long way around because you could also simplify this into 2 plus x to the negative 1 and use the power rule. So because you can simplify and use the power rule, I wouldn't say that quotient rule was the best method. I mean, I guess that's kind of subjective, but if we're talking efficiency, simplify and then power rule is definitely a lot faster. So we won't necessarily eliminate this one, but if we find one where quotient rule would be a better choice, then we're going to ditch this one. All right, choice C. We've got a function inside another function, so this is again chain rule. Choice D, we've got a function in a function, but we've got it in the context of a quotient. So because we've got a quotient here and we cannot simplify this quotient into anything, that means that we're going to have to use quotient rule here. There's no choice about it. So I'm thinking the one where we have to use quotient rule is a better choice than the one where we could use quotient rule but don't have to. So let's go with choice D. For this calculator-based free response problem, we've got a table of values for f and its derivative, and we've got this g function that's defined as f of 2x minus x squared. A lot of tasks here, the first of which is to find g prime of negative 1. So if we take the derivative of g in general, that's going to require the chain rule. So we have the derivative of f of something, that's going to be f prime of the something, so f prime of 2x minus x squared, times the derivative of the something, so times 2 minus 2x, and then g prime of negative 1, we're just plugging negative 1 in for all of these x's. So if we do that, we've got, let's see here, 2 times negative 1 is negative 2. This is subtracting positive 1. So this is negative 3, f prime of negative 3, that we have when all the dust settles here, and we'll figure out what that is in just a sec using the table. Next to that, we have 2 plus 2, which is 4. All right, so what is f prime of negative 3? Looking that up in the table, that has a value of negative 2. So this is negative 2 times 4, which is negative 8. On this problem part, we're told that g double prime of 0 has a value of 0. Based off of that, we want to know the value of f double prime of 0. Well, the way we can do this one, since the g function is partially defined by using the f function, perhaps in the process of finding g double prime of 0, we'll end up with an f double prime of 0 in there somewhere, and we'll be able to solve for that when we set this equal to 0. So let's start by just finding g double prime of 0, and we'll go from there. Now, we already figured out g prime of x. Recall from part A that that was f prime of 2x minus x squared times 2 minus 2x. So that was g prime of x. To find g double prime of x in general, we're going to need the product rule, u prime v minus, plus uv prime. And let me set up the box and ribbon to help me negotiate that. So I've got my first factor, f prime of 2x minus x squared. And then after that, there's that 2 minus 2x. So the derivatives of these now, derivative of this f prime stuff, we're going to need the chain rule on this one. So the outer function is f prime of something. The derivative of that is going to be f double prime of the something, 2x minus x squared. But now I have to multiply by the derivative of that inner function, so that is again going to be 2 minus 2x that I'm multiplying by. Now over here, this 2 minus 2x, this is v prime, the derivative of this is just going to be negative 2. All right, now before I put it all back together here, let me just plug in 0, because we're doing g double prime of 0. Let me plug 0 in inside the box and see what I'm looking at. So this f prime business in the upper left, if you plug 0 in for x, you're really doing f prime of 0, which looking that up in the table gives us 4. Next, 2 minus 2 times 0, that's just going to be 2. Down here, this is going to be f double prime of 0 times, this is just going to be 2 here, so 2 times f double prime of 0. And then finally, negative 2 is a constant, so no need to change that. And let me make that negative 2. There we go, negative 2. So now let me use the ribbon to put this back together. I'm going to have 2 f double prime of 0 times 2, so that's 4 f double prime of 0. And this, by the way, is what g double prime of 0 equals. So 4 f double prime of 0. And then we're going back the other way. This is 4 times negative 2, and we're adding all that. So plus negative 8 is minus 8. And we said that all of this stuff should equal 0. So now just solving for f double prime of 0, which is really what we wanted in the first place, adding 8, dividing by 4, we get a value of 2. For this part of the problem, they're asking if there's a c value between 0 and 3 such that g of c is 2. So this is invoking the intermediate value theorem if you're asking for a certain output value given a range of x values. And for that, we need to know whether we are continuous for this function along this interval, and also whether 2 lies between g of 0 and g of 3, the beginning and the ending y values of this function on this interval. Let's tackle the continuity piece first. Do we know for a fact that g is continuous on the closed interval from 0 to 3? Well, they told us that g is defined as f of 2x minus x squared. We know that 2x minus x squared is continuous and differentiable. It's a polynomial. We also know that the f function itself is differentiable, twice differentiable, in fact. So, because f is differentiable and so is 2x minus x squared, we can conclude that anything created out of that, like the g function, will also be continuous. All right, so we've got continuity established everywhere, not just 0 to 3, but 0 to 3 is included. We also need to know what g of 0 and g of 3 are to see if 2 lies between those values. So g of 0, that's really the same as f of 0, because that's 2 times 0 minus 0 squared. And f of 0, we know from the table, right here, is going to be negative 1. Next, we look up g of 3 from the other endpoint. So that's going to be, let's see, f of 6 minus 9, so negative 3, f of negative 3. F of negative 3 in the table looks to be 5. Is 2 between negative 1 and 5? Sure is. So therefore, we're guaranteed by the intermediate value theorem that g of c does equal 2 for some c value on the open interval from 0 to 3. For this last part, we're defining h all of a sudden as some function whose derivative is h prime equals 4x e to the x. We want to know what x value on the interval 0 to 4 makes the instantaneous rate of change of h, which is, by the way, modeled by this function here, equal the average rate of change of f over the interval from 0 to 4. So basically, we need to figure out where h prime of x equals whatever the AROC for f is. In order to do that, we need to first figure out what the average rate of change for f is over this interval. So that would be f of 4 minus f of 0 over 4 minus 0. And we can look all of this up in the table. F of 4 is 7, so we're doing 7 minus f of 0, so minus negative 1 or plus 1. 7 plus 1 is 8. Dividing that by 4 gives us 2. So basically, we want to know then where h prime takes on a value of 2 on the interval from 0 to 4. So let's use the grapher for this piece. So here I am in my y equals. I've entered in h prime and my average rate of change, which we said was 2. Now if I go to window, I want to make my window 0 to 4 because that's the only window I care about. Let me do zoom 0, zoom fit, and hopefully we can see a good intersection. So there's my exponential h prime function. And here is somewhere is my equals 2. It's somewhere down here. It's kind of hard to tell, but based on this scale, it's got to be down there somewhere. Let me make my life a little bit easier. So I'm pretty sure I'm not going to actually cross this graph after 2. So let me just readjust my window. Let me go from 0 to 2 and zoom fit that. It'd be nice if I can just really see the intersection. There we go. So I mean, I could have done second trace option 5 and done intersect, enter, enter, enter before, but now I can really see where that intersection is, so I feel a lot better about doing this. So let me go ahead now, second trace, option 5, intersect. Let me move my spider over to the intersection that I can actually see. Enter, enter, enter. And that comes out to about 0.5352, it kind of looks like. Yep, 0.352. There we are.